So in this lesson, we're going to be looking at quotients of polynomial functions. We're going to explore graphs that are created by dividing polynomial functions, and by doing so, we're going to learn how to determine vertical asymptotes, horizontal asymptotes, and oblique asymptotes. I'd also like to introduce my star student.
Hi, class.
So just as a recap, what is a rational function?
I have no idea.
Well, Sammy, a rational function is of this form where f of x is equal to h of x over g of x, and h of x and g of x are polynomials.
Okay, let me think. So, a rational function is when you divide two polynomials.
That's absolutely right. So now, what are some general properties or key characteristics of rational functions?
We always need to find their intercept.
Yes, we definitely need to look for x and y intercepts. We also want to examine end behaviors like we did last unit, and we want to look at any holes and or asymptotes. And as a reminder, we have holes anytime we can factor out a term from the numerator and denominator and they cancel out. So for asymptotes, we're going to talk about three different types. If we remember, when we're looking for a vertical asymptote, we want to set the denominator to 0 because that's when it's undefined, and then solve for x, and that's going to give you a vertical asymptote. When you're solving for horizontal asymptote, we want to find it by examining x as it approaches infinity from both sides, so positive and negative infinity. And we'll talk about this in greater detail later on. The third asymptote that we're going to look at is oblique asymptotes, and we'll also look at that later on. So in our first example, we're going to determine the key characteristics of this function and sketch the graph. So first thing we want to figure out are the intercepts. So our y-intercept is going to be found by setting x to 0. So in this case, we're going to get 0, and our y-coordinate is going to be negative 4 over negative 2, which is positive 2. And our x-intercept can be found by setting y to 0. So I'm just going to do this on the side, make y equals 0, and your denominator is going to multiply by 0, so that's gone, and so you'll have x squared is equal to 4, so x could be equal to plus or minus 2. So your possible x-intercepts right now are negative 2, 0, or 2, 0, maybe. So hopefully when you first looked at this function, you knew that you can factor this. So the top looks like a difference of squares. So you'll get x minus 2, x plus 2, and the bottom is just x minus 2, so you're able to cancel out the x minus 2, which indicates that there may be a hole at x equals 2. And so our resulting function is just going to be f of x is x plus 2 with a hole at x equals 2. So because we have a hole at x at 2, this cannot be our x-intercept. So our x-intercept is just really negative 2, 0. The resultant graph looks like this. So it's just a linear function x plus 2 with the y-intercept of 2, and at 2 there's a hole. So a graphing calculator won't actually show you the hole, but it will show you this as your rational function. So this is called a simplified rational, which is actually a polynomial function. Okay, for our next example, we have f of x is equal to x plus 1 over x minus 2. So first thing we want to do is find our x-intercept, x and y-intercept. So our x-intercept is when we set y to 0, so the denominator is going to cancel out, and then solve for the numerator, which is x is equal to negative 1. So we know negative 1, 0 is going to be our x-intercept, and we know we don't have any holes in this case because nothing's canceled out. Y-intercept is when we set our x to 0, so we'll just get 0 and negative 1/2. as our y-intercept. We can also see that looking at our denominator, what would make that equal to 0? So x cannot equal 2. So that is going to be our vertical asymptote. And we know it's not a whole, so it must be a vertical asymptote at x equals 2. Now we're going to check if we have any horizontal asymptotes. So previously we've seen that if we had a function of the form 1 over x, or that reduces to 1 over x or 1 over x squared, we know that your horizontal asymptote is 0. But in this case it doesn't. We have a linear function on the top, a linear function on the bottom, and your highest power is just going to be x. So if you divide out, so quickly, your horizontal asymptote, we're going to take the highest power, which is just x, and you're going to put everything over x. X over x minus 2 over x. And now we're going to set x to a really high, x is going to, like a really high number, so it's going to be approaching infinity. So as it gets bigger, this you can already see is going to be 1. This is 1 as well. But as it gets really big, 1 over a really big number is going to get closer and closer to 0. So this is going to be 0. 2 over a really, really big number is going to, as it's increasing, is going to approach 0 as well. So your horizontal asymptote is just really going to be 1 over 1, which is 1. Had this question been 2x plus 1 over x minus 2, our horizontal asymptote would have been 2. So really you're looking at the highest power, and they should be matching. So you should have the same power on the top and bottom, and you're looking at the coefficients. So if it was 2x plus 1 over x minus 2, your horizontal asymptote would be at 2. 2 over 1, which is 2. Okay, so now looking at this graph, we can see that we have a vertical asymptote at x equals 2 and a horizontal asymptote at y equals 1. And we know what quadrants the function exists by plugging in numbers and just examining the end behavior. So now for the next example, f of x is equal to 2x over x plus 1. Of course, we want to figure out our x-intercept and y-intercept. So our x-intercept is when we plug in 0 for y, and that will cancel out our denominator. So we are left with 2x is equal to 0. So x is equal to 0. So at 0, 0 is our x-intercept.
But wait, our y-intercepts are also 0, 0.
That's right, because when you set x to 0, you're going to get 0 on the denominator, on the numerator, and 1 on the denominator, which will give you 0. So yes, you're right. So now let's find our vertical asymptote. We can find it by setting the denominator to 0.
I think it equals -1. Are you going to do the HA?
Yes, let's look at our horizontal asymptotes. So to find that, we're going to look at the powers. So we have a linear function on top, 2x. And on the bottom, we have x plus 1, right? So that's also linear. And then, so they do match. And so now we're going to take the coefficients before the x. So 2 over 1 is going to be 2. So we have a horizontal asymptote at y equals 2. So now looking at the graph, we know we have a vertical asymptote at x equals -1 and a horizontal asymptote at y equals 2. And we can also see that we have intercept at 0, 0. This example, f of x is equal to x squared plus 4 over x plus 1. So first thing we want is to figure out our x and y intercepts. To find our x-intercept, we're going to set y to 0, and then the denominator cancels out. We're going to get x squared plus 4 equals 0. Bring the 4 to the other side, and you'll get x squared is equal to -4. So we can't take the square root of a negative number, so we don't have any x-intercepts. To find your y-intercept,
we're going to make our x equal 0.
when we make x equals 0, we get 4 over 1,
4 over 1.
which is just 4. And now we're going to look at the denominator to see if there's any vertical asymptotes, and we can see that we have one at x equals -1. And we're going to ask ourselves, do we have any horizontal asymptotes? So we notice the power on the top is quadratic. It's to the power of 2. And then on the bottom is linear to the power of 1. So the powers don't match. The degrees don't match. So we don't have any horizontal asymptotes. Now since the top, the numerator, is 1 greater than the denominator, this actually lends itself to having an oblique asymptote. So an oblique asymptote is an asymptote that's going to be a line. And the way to find this line is to divide our polynomials. So I've set this up. Now we're going to say how many times does x go into x squared? So that's x times x plus 1 will give us x squared plus x. Subtract that, and we get negative x. Bring down the 4, so negative x plus 4. How many times does negative x go into x? And that's -1. So we're going to get x minus 1 up here. And we may get a remainder. Doesn't matter. We're kind of done at this stage. You're really only worried about this number right there. Once we have that, that's our oblique asymptote. Now let's see what this looks like graphically. So here we have our vertical asymptote at x equals -1, and our oblique asymptote, you can see, is at y equals -1. So that's just y equals x, but it has a y-intercept at -1, so transformation of a vertical shift down 1. And we can also see we have our y-intercept at 0, 4. So just to summarize, if f of x is a rational function, so it's of the form p of x over q of x, we know that f of x has holes if p of x and q of x have any common factors that you can cancel out. You have a vertical asymptote when q of x is equal to 0. Horizontal asymptotes are determined by coefficients of the highest powers of p of x and q of x. And f of x has an oblique asymptote if p of x is 1 degree higher than q of x. And you would find your oblique asymptote by dividing out your polynomials.
Thanks for watching. Thank you for watching.